Okay, ready for a quiz? Sure, why not? Right. Sorry. If that helps.
Now we're doing a quiz. He didn't see. Not yet.
It's graded on the questions, right?
Yeah.
And a lot.
They didn't have to ask all of them. So they didn't. So we'll get.
Some of them, like, just,
Oh, yeah. What did they say? Okay. Questions?
some of them have a solution, like, anything about it.
They're not-
Yeah, some of them determine the data, that's it, like. Is that a neighbor?
Now remember, it could be more than one. That's why that's four or eight.
Okay, everybody ready to upload?
Ready.
Don't overthink it. Okay, everybody got it uploaded, right? It's time to upload. Get started. Good, good. Everybody struggling? Sound totally right. So you know you can do it directly to your phone to catch up. Gates. Up. Excellent. Okay, so the first one, CO2, is an element, molecule, or compound. Compound. Okay, so we got those who say compound, raise your hand. Those who said molecule, raise your hand. Those who said molecule and compound, raise your hand. Molecule and compound is correct. Okay. So the next one, S8, is in a compound. Anybody thinks it's a compound? Raise your hand. A molecule. Okay. A element. Anybody not vote? How many think is an element and a compound? How about an element and a molecule? Okay, the answer is it's an element and a molecule. Right? It's a polyatomic element. Okay, the next one, sodium chloride. Is that a compound? Compound?
Yeah.
Is it a molecule?
Yeah.
Yeah, it's a compound and a molecule, right? What is the definition of a molecule? Two or more atoms, right? Two or more atoms. So if it's like, is it an element? You guys have to, come on, have to pump it up, right? Okay. Gold, AU. AU stole my gold.
Element.
Element, compound. Molecule. Okay, guys. We know you all got this one, right? Okay, number E. Letter E. We said element, and molecule, right? Element and molecule. Compound has to be two or more different, right? Okay, so accuracy. Accurate or precise? So these are our patients, your readings. This is the first one, this is the second one, this is the third one. Is the first patient accurate?
Yes.
Is it precise?
Yes.
The next patient, accurate?
Yeah.
Yeah.
Yes. Precise?
No.
Third patient,
No.
all over the place. Is it accurate? No. Precise?
No.
Okay. So accurate means that we are hitting our target, right? Think about when you're playing darts, you know, you hit the bullseye, you know, so you have to hit the bull to be accurate, right? Okay, precise means that they're all close together. So instead of hitting the bull, you hit 20 all the time, right? Okay, so I remember where we left off. It was like forever since we had lectures. Okay, so before I start with the lecture, I sent you guys an email. Did you guys get my email about physics?
Yes.
Yes. Anybody interested in taking physics? It's right after this class, as a matter of fact. All right, good. Did you sign up? Okay, make it to the class, and then we'll get you signed up. They're doing a lab today, so. And they'll be next door. Okay. Yeah, we're trying to get these classes up and running so we can get you guys through your programs and degrees. But you know, if you guys aren't signing up, we can't get you through your degrees. And I know that some of you guys are taking it in the more. You know, I'm not opposed to coaching, right? I'm like, hey, come on over. If you don't like what you're doing, you don't like what you see in there, you may find something better here. So
But is it a full 18 or a 9?
it's actually 16.
But that's
So,
only for like the first part, right? Like the first, because
Yes.
there's 1 and 2.
yeah, so there's physics 2, which is for, let's say if you're planning to be a doctor, if you're planning to go into kinesiology, if you're planning to go into something else, environmental sciences, along those lines. So you'll be taking physics 2. You can take physics 2 and 2B, right? I think kinesiology only has to take the first semester. The second semester, if you're planning to go to next.
You guys have a second semester too?
Yeah, we're gonna get it offered, but we need to see how people do the first semester And so then I have to go and fight my admin to get it on the books. And so we're trying to get out of the habit so I don't have to fight as much all the time. But every semester, pretty much the semester before, I'm fighting to get the classes on the books. Like we teach organic chemistry here, right? We need to get it on the books this semester because last semester I only had 5 students face to face at the 1 series. So we can justify it for 5 students. So they wouldn't let me put it on the books. But I'm gonna try again next semester, right? And so if you guys need OCHEM.
I don't need it, but I'll take it.
Yes, actually, it's in some programs, and this is the other thing that a lot of students don't realize. So you often just look at your degrees here, right? You need to look beyond here, right? Because for instance, if you guys are in plant science, then you need it when you get to the next level, right?
Yeah.
And so it doesn't make sense to me. It doesn't make sense. You can take it here for a whole lot cheaper than what you're taking it there for.
Like 10%.
Exactly. And you have a kick-ass instructor too. So, you know, I'm like, that's another bonus. Yeah. So I don't know what I did. And absent-minded instructor, so I keep losing my little clicker. So if you guys see my clicker, it's here somewhere. So that's what happens. I walk around. Oh, there it is. See? Okay, so we've talked about physical change. Have we talked about physical change?
Yes.
Yeah.
Chemical.
Yeah, physical versus chemical. Okay, just making sure. We talked about homogeneous versus heterogeneous. We have not talked about homogeneous versus heterogeneous. Let's talk about homogeneous versus heterogeneous, right? So when we talk about something being pure, right? We can have a pure compound, right? But if I mix 2 pure compounds, it's no longer pure. It's considered to be a mixture. Let me give you an example. So if I put sugar and salt together, right? They look the same. They're not the same. So we would call that a homogeneous mixture or homogeneous. Homo meaning same, like homosexual, same sex, right? If we have salt and pepper, do they look the same? No. And we mix them together, can you tell the difference between them?
Yeah.
So that's an example of a heterogeneous mixture. Hetero meaning different, like heterosexual or a girl, right? Different. Okay. So when we talk about mixtures, they can be homogeneous or heterogeneous. Now this is dictated by what we see, right? Does it, if it looks uniform, right? It's all based upon what we see. That's how we describe it. It's upon vision. So if it looks uniform, it's homogeneous. If it looks different, it's heterogeneous. Have you guys ever put alcohol and water together? Yeah, when you guys were diluting with your dad's bottle of vodka that you were drinking out early or something like that? Oh, no, he's not gonna admit to that right now. It's recorded. So, yeah. Okay, so when we put things like alcohol and water, you can't tell the difference, right?
So
They really couldn't tell the difference until they tasted it, right?
Or if it's
Until it freezes, that's right. Right, so they really couldn't tell the difference otherwise, right? So you were sitting there able to bring it back to the level that your dad had marked out on the bottle, right? Okay, so in that context, would that be homogeneous or would that be heterogeneous? Homogeneous, right? So if I put orange juice and milk together, have you guys ever put orange juice and milk together?
yeah.
In school, right? You guys can just imagine what that's gonna look like, right? Is that gonna be heterogeneous or is it gonna be homogeneous? It's gonna be heterogeneous, right? So that's examples of it, right? You guys kind of got an idea of it? Okay, now the things about mixtures. Mixtures can be separated by their physical properties, right? So like for instance, if we have water and alcohol. So if I wanted to get all of that alcohol back that I had diluted, I can distill it. I can heat it up because water boils at 100 degrees Celsius and alcohol boils at 89.6 degrees Celsius. So long as I keep it below 100, but higher than 89.6, I'm able to recover the alcohol, right? And then I can get my 151, proof alcohol that I've been drinking all day, right? So, and this is the same case with heterogeneous, or homogeneous and heterogeneous. You should be able to recover from both, right? So if we take a look at this, here's an example. Oil and water. Okay, here we go. Chemistry. Oil and water. So here we we have an example of oil and water. You can see the oil bubbles in the water, right? So heterogeneous or homogeneous? Hetero, okay. And Gatorade, which we know is just sugar, it's electrolytes, it's water,
So
electrolytes. Okay, so in that case, homogeneous, heterogeneous. Homogeneous. Okay, so if we look at matter, we can kind of separate matter into two forms. Is it pure or is it a mixture? Right. So if it's pure, then we know that we can also separate that even further, right? So we can use those physical properties. I mean, sorry, if it's a mixture, we can separate it even further. We can use those physical properties to separate it. So we can use those physical properties to sit there and separate it. But when it's a pure substance, if we want to separate those elements, right, the only thing that we can use is a chemical property. Okay, so let me give you an example, right? A piece of wood. You guys see a piece of wood?
yeah.
Is that homogeneous or heterogeneous? Homogeneous, everybody's homogeneous or heterogeneous? Well, first off, it's a piece of wood. Okay, so that's, I kind of set you up for that, right? So we have the bark. It's gonna be a little bit different than the inside of the wood, right? So if you sit there and you think about it, if we have the bark still on the whole thing, then it's probably not gonna be homogeneous, it's gonna be heterogeneous, which means that it's composed of two different types, right? Although they're similarly made, there are differences between them, right? Chemically, there's differences. Now, if I take a piece of wood and I burn a piece of wood, am I able to get wood back? No. So would that be an example of a chemical reaction or a physical reaction? Okay. So rule of thumb, if I can't get it back, it's going to be chemical, right?
Oh.
So if I can get it back, it's going to be physical. So when we did our Mentos experiment, right, and we basically allowed the carbon dioxide to escape the bottom. That's what we were essentially doing. We allowed the surface area to be there, kind of speeds up the reaction and everything like that, or speeds up the physical reaction, right? But if I really wanted to, I could put like a balloon on top of this to collect all of the air that was escaping, and then I can kind of shake it up again and mix it back into the soda, right? So technically, I can recover it and put it back, right? So is that a physical reaction or a chemical reaction? Physical. So if I can recover it and put it back in, then that means it's going to be a physical reaction. Now I want you to think about this. Do you like cake?
Yeah.
Sure. Okay. Of course, I'm talking about sweet cake. I'm not talking about sour cake. We'll talk about sour cake later. I'm talking about sweet cake.
Yeah.
Sweet cake. Okay. Who knows how to make a cake? Anybody know how to make a cake? Okay. What do you put in a cake? I put egg. I put flour, water, sugar, a lot of sugar. No sugar?
No sugar.
No sugar, man. You gotta have cake, you have to have sugar, right?
You got substitutes. You got monk fruit stevia, you know?
Okay, okay, so we're getting fancy now. We're putting monk fruit in the stevia. Okay, so, and then what do we do with it?
Mix it.
We mix it and we bake it, right? So, can you guys recover the sugar from the cake? Just the sugar?
No.
Can you recover the egg from the cake?
No.
Okay, so is that a chemical reaction or is that a physical reaction?
Chemical.
Okay. So if I have ice cube and it melts all over the floor, is that a chemical reaction or a physical reaction?
Physical.
Okay. So I can recover it. I put a bucket underneath, I can recover it, put it back in the ice tray. That'd be kind of nasty, but you know, I can do it, right? Okay. So let's see. What about, have you seen glow sticks? You guys know what glow sticks are?
Yeah.
Okay, so if I crack open a glow stick, right? Is that a physical reaction? Or is that a chemical reaction?
Chemical.
Do you agree? Sure. Okay, so that's the difference between physical properties and chemical properties. Some examples of physical properties, that's going to be your density. It's going to be the color. It's going to be the hardness. It's going to be the melting and boiling point. It's going to be whether or not it conducts electricity. Right? Those are all considered your physical properties. So, here's an example. We have candle burning. sorry, not a candle burning, wax melting, right? And then because we can collect the wax, get it back. Candle burning would be chemical, right? And then water boiling. Okay, we talked about chemical properties. That's flammability, that's acidity, that's reactivity, that's heat combustion. Yes. Okay, so here we have an example of rust. Right? That's definitely chemical, right? Because we have iron being oxidized to make rust. And then we have chrome, which isn't able to be oxidized to make rust. Right? So if we put a little chrome in there, all of our iron is kind of safe from all of that rust. Okay. So here's some examples of a chemical reaction. So the first one is copper nitrate, right? So we have nitric acid with copper, forming copper nitrate. And so it makes this brown gas, poisonous brown gas, which is the gas is nitrogen dioxide, which is really bad for us. And the second one, like I told you, well, this is a match version instead of a piece of wood. Cellulose match, piece of wood, cellulose, not cellulite, cellulose. Okay, so and then we have our red meat cooking, right? Chicken. Then we have bananas rotting. And that you guys understand how bananas rotting would be a chemical reaction. You know, smell alone should tell you that, right? So ways that we can typically tell a chemical reaction has occurred. I want you guys to think about it. I want you guys to start answering. So what are signs of a chemical reaction? Give me one. Give me one. Give me one. What were we just talked about?
Fruit rotting.
Fruit rotting. So what is one of the things about fruit rotting?
So I can oxidize.
Okay. Okay, but more specifically, how can you tell that fruit has rotted?
Smell and color.
Smell and color. So we got to change in color and smell. So we have odor and smell. So those are two. Okay, give me some more.
Taste too.
You're not supposed to taste something. We can't use that one. Of course, taste too, but we said flammability, right? If it catches on fire, right? Okay.
This is
So-
volume.
Loss in volume?
Yeah.
Not necessarily, right? Because if we think about how ice is, right?
Yeah.
And if we had ice that had already expanded and melted, it's going to lose volume, right? Yeah. Okay. Yes,
Change in texture,
change in texture. Elaborate.
like when bananas are, they start getting all mushy and squishy.
Okay, so change in texture. Okay. Anything else? Yes. Exothermic reaction. Okay, so heat being released or energy being released, right? Acidity. Okay, so what do you mean?
Like, well, this is relative. Normally certain vegetables and fruits when they rot, they do have kind of soury.
That's sour. So you were talking about that taste again, right? Oh, so you guys are on the same lines, okay? Okay, so anything else?
But does it attract like flies?
That doesn't have anything to do with it. That's just what flies like. Flies like fun. So,
Toxicity, but I don't know if that underlines what taste.
toxicity it can be used as a yeah. So I'm gonna poison you. Yeah. Okay, yeah, that'll work, you know. But that's not what we're gonna do it live, right?
Hope not.
Okay. Something else. So let me recap what you guys told me. So we had toxicity, we had acidity, we had odor, we had heat, we had combustion, lighting up.
Color change.
Color change, that's right. Yep. And God said, let there be what? Let there be light, right? Let there be light. The glow stick, right? Glow stick glows, right? That's an example of chemical reaction. So all of those are examples of chemical reactions that we can sit there and determine that a chemical reaction has occurred. right? And so we need to be able to sit there and use those tools, fine tune those tools to determine whether or not there are chemical reactions. So let's talk about safety, right? So because we know that all of this, right, one, because for instance, we have no light, right? Here. Nice rocks. We have no light. Okay, so here in this context, why do you not have light? What was happening under these circumstances? No. What's happening? So we know that there's electricity. What is electricity made up of? Anybody want to know? Anybody know? No, it's not protons. Think about it. Electricity, would it be made of protons?
No.
Would it be neutrons?
Electrons.
Electrons, right? So we have electrons that are flowing through the wire. So they're being transferred to the wire, right? So that's also just an example of a reaction occurring. So when we close the wire, right, electrons are able to continue to flow, right? When we close it so they actually touch, it's able to flow. And then when we get to a bulb or whatever, there's resistance. And as a result of the reaction, a chemical reaction, we get light. So, and that's also part of the reason why bulbs eventually, they die and burn out, right? Because it is a chemical reaction. You're putting all these electrons in there, you're pumping it up, and eventually you're going to snap that wire, so you're no longer able to sit there and get that. Okay. So light, so that's one example. The other example is the emission of light. So when we crack the glow stick, right, it actually is a chemical reaction that emits light. And then as soon as that glow stick dies, what happens? Do you still have light? No, right? It dies out. You don't see the light. So then you've all used up all the chemicals that would allow us to have emissions. So you guys will actually be making a glow stick. That's kind of, towards the end of the semester. It's a new lab. It's a tester. You guys are you're going to be my guinea pigs. Yeah, it turns out. Yes.
When it comes to chemical changes, depending on the circumstance, does it display all the qualities, or is it
No.
just give or take?
It could be either one. It could be one, it could be the other, it could be multiple. So good questions. Very good questions. Okay, so if we look at this, this is the old school. This is called the National Fire Protection Agency symbol, right, or diamond. Okay, it lets us know, and it also lets firemen know what type of hazards we have in our lab. So on the back of bottles, they basically will have this, right? So here in the white diamond, it is for a specific hazard. So if we have an oxidizer, oxidizers are known to cause things to ignite, to catch on fire, right? If it's an acid, if it's alkali, if it's corrosive, if you don't want to use it with water, right? So those are the ones you want to pay attention to, right? Because we get a lot of moisture now, lately it's been very humid. So just being out in the humidity can cause something to explode, right? And then also if it's radioactive. Okay, here in the yellow, this is your reactivity. The higher the number, the more reactive it is. The lower the number, the least reactive it is. So if it's at 0, it's stable. If it's at 1, it's unstable if it's heated. If it's at 2, it's a volatile chemical, meaning that it can ignite like that, right? If it's 3, if you shake it, if it's shocked or heated, it's going to detonate, it's going to explode, right? And then 4 means it's definitely going to explode, right? So if you don't handle it appropriately, it's going to blow. Okay, so the red is a fire hazard. So again, the higher the number, right, the lower the flash point. You guys know what flash point is?
The point at which it'll go off or ignite?
Yeah, it's the point where it'll ignite. So if it's a 4, it's below 70 degrees Celsius, right? We live in the valley. How hot does it get here? Pretty hot, right? So we try to avoid having chemicals that are, that are 4s in our lab, although we have a few. So they have to be refrigerated in that case to make sure, particularly in this room, because this room gets hot. That room gets pretty hot as well too. So if it's a 3, then it's below 100 degrees. So that means that its splash point is below 100 degrees Fahrenheit. Right? So 100 degrees Fahrenheit is about what we have in our normal weather, right? So things would just automatically catch on fire. Okay, above 100 degrees Fahrenheit, but not exceeding 200 degrees Fahrenheit. That will be a 2, and then above 200 degrees Fahrenheit. And then if it's a 0, it's not going to burn. Now you don't need to know specifically. All you need to know is like the higher the number, the worse it is, right? The higher the number, the worse it is. Okay. So the next one is a health hazard. So a health hazard, it's along the same lines. If it's a 4, it's deadly, right? So you definitely want to be wearing gloves. You want to be wearing your PPE. You know, if it's a 3, it's extremely dangerous. If it's a 2, it's hazardous. If it's a 1, it's slightly hazardous. If it's a 0, it's normal material. So like sugar would be a 0, right?
Yeah, like on the health test, would a 4 or a 3 start to require people to go like hazard?
It depends. It depends on the quantity you're using and what you're using. So typically hazmats are, so it can be, like I said, it's usually based upon quantity. Okay, so now the national, the NFPA is being phased out, right? I mean, they were great and everything, but I mean, it didn't tell us enough about the chemicals that we were working with. And as you guys are being young scientists, you want to have an idea. It's going to give you cancer, it's going to give you a heart attack, it's going to kill fish, it's going to kill, you know, so you want to know a little bit more, right? So we've moved over, and this has been by the year, supposedly it's supposed to be by the year 2025, all the chemicals on the back of them should have the global harmonizing system pictograms on them, right? And so it's also called the GHS. So the GHS are all of these little symbols, and they kind of tell you what they mean. And typically they're labeled what they are, and then they give you the image itself. Like, for instance, if you see the heart exploding, right? So that means it's a health hazard, right? That means it's a carcinogenic, right? We know a lot more about chemicals today. We know a lot of them cause cancer. And so we also have an idea about what levels you should be working with and how long you should be working with it. If it's a mutagen, right? You don't want your kids to come out with 2 horns and a tail or anything like that. You may want that, but you know. So we want to make sure that we are aware that the type of hazards that are associated with it. Okay, so these images helps us kind of dictate what type of hazard we're working with. And then usually they tell you specifically. So if it is a mutagen, it'll show that emblem and it'll say mutagen. So we know that it's a mutagen. Okay. So if it's flammable, right, it's going to have that image. So these are all examples of how it can be flammable. Right? If it has an exclamation point, so that means that basically it's going to be an irritant. It's going to irritate you. Your skin is going to itch off and everything like that. Not completely off. It's going to scratch you. You know, very sensitive, you know, stuff like that. And it could be a little bit more acute, right? You have that acute toxicity, right, associated with it, which means, again, it's harmful for you, but it may not necessarily kill you, but it's going to give you some discomfort, right? Gas cylinder, basically that means gas is under pressure. If it's corrosive, it can be corrosive to your skin, it can burn, it can do eye damage, you know, it can be corrosive to metals. Exploding bombs. So if you see that, you probably don't want to play with it, right? Because that means it's going to explode on you. And if you have the flame over a circle, these guys are oxidizers, right? So they help fires get started. You want to avoid that too. Although we have quite a few oxidizers in labs. They're so much fun to play with, you know. See your fireworks, right? Yes.
Isn't methane an oxidizer?
Methane? No, methane isn't an oxidizer. Methane is a flammable gas, right? So it would fall under the flame, right? Yeah. Okay. Okay, so then we also have environmental factors, right? And you notice it says not man, right? So that one has been revised, and they continuously argue about it because a lot of the environmental agencies want to, environmental protections want to make that mandatory on all the chemicals that may cause damage to the environment. But there are people that are in those disciplines, they don't want to have it on their environment. So for instance, a lot of pesticides, right? So they would all have that on.
Yeah.
They don't, right? Because that's one industry that lobbies against it. Now, see, this is one of the bad things about everything is that, you know, when you get science and politics, they often will collide, right? And so as a good scientist, you try to avoid the politics, you try to think level, right? So you want to think level because you have to make sure that you're protecting yours, right? The people that are working for you. And so you always want to think level, you want to think about what's good for the people that are working for you, right? Now, as a politician or the CEO sometimes, or CFO mostly, right? So they don't often think about the people. And so they don't think about the science. They just think about the profit or they think about what their goals are, right? You know, I want this election. You know, this is for benefit of me. So you're going to come in conflict. And that's just the way it's going to work. And, you know, as much as we want to change that, we want to get politics out of science, it's never going to happen because we're such a political nation. And that's whether you're on one side or the other, we're still going to be a political nation, right? And that's the way it's going to be. You got to accept it. So as good scientists, you always want to think about the people that you're with, right? Think about yourself and think about the people that you're with. And often I figure that all you guys are going to be, you guys are in this class, you guys are going to be the leaders, right? You guys are going to be the supervisors, and, you know, and eventually get to the point where you're going to be the one that owns the company, right? So you want to think about those things when you yeah.
Oh, no.
Anybody can have a comment, right? So that's my political soapbox. Try to keep politics out of science because it gets really messy, right? But you can't avoid it. So you got to stay on top of it. And you got to be prepared to use science to disprove what's being said. Okay, last thing is the skull and crossbones. What do you think that means?
Looks like that.
I'll leave the bill down.
Yeah, fatal, lethal, toxic, yeah. So you see that? Worry about it. Okay. So,
Isn't it Msds?
that's the old way. It's material data sheets now.
Sorry. Oh, yeah. The lobby gets right now, trying to get it out.
Okay, so when you're working with chemicals, you also get, it used to be called the Msds, the Material Safety Data Sheet. Now it's just called, often just called the Materials Data Sheet. So on there, it tells you about the product. It tells you what the product looks like. It tells you your GHS classifications, and it'll show you which ones that'll be depicted on there. And specifically, it'll tell you what's going to happen. It'll tell you if something happens to you, see it in your eyes, what you should do. Okay. Yeah. Tells you the chemical formula. It's often just going to tell you its molecular weight. And it's going to give you its CAS number. CAS number is a number that is used to identify that chemical. So there's this database that's kept by every country in the world. It uses the same CAS number for every different chemical. gives you the first aid measurements. Tells you, okay, in case of a fire, this is what you have to be concerned about. So if it's accidentally released, let's say you spilled it on the ground, it tells you the precautions, what you need to do to handle it. What you need to do in that case. So if it's personal precautions that you have to worry about, what you should be wearing. Don't breathe it in, the environmental protections. Tells you the handling and storage. It tells you the exposure controls, the personal protections. Tells you physical and chemical properties. Stability, toxicity. Ecological information. That's, in other words, how it's going to affect the environment that we're talking about. How it should be disposed of. Transportations, regulations. Okay, so again, as a good scientist, anytime a new chemical comes into your lab, you should always have access to the Msds, right? So I came into the lab and we have a huge database, right? But not every faculty member has access to the database. So I had to go do inventory. It's a pain in the butt. I'm doing inventory on a lot of chemicals. And then you have to find the SDSs that are associated with it. And which again is a pain in the butt to sit there. So, and we have links associated with it. So every chemical that's in this lab, we have a link that's associated with it. So what I'm going to do is I'm going to make a copy so that you guys will have that link. And it's part of your responsibility to know what chemical you're working with before you start the lab. Right? Handle, mainly how it should be handled, kind of how's it going to act if it gets in your skin and on your body. Okay? So that should be something standard that you guys look at. Okay. Extensive properties. Okay, extensive. So that's going to be dependent on the matter that's present, on the amount of matter that's present. So in this case, you're going to be thinking about the mass, the volume, okay, the heat. Okay, the intensive properties, right? It isn't dependent on how much is present. So that's going to be like the density and the temperature. So for instance, regardless of how much water you boil, what's going to be the boiling point of water? 100 degrees Fahrenheit. So now it's going to take a lot longer to boil, a big old thing of water compared to a little thing of water, but still that temperature is still going to be the same. Okay. Now, regardless of how much water you have, the density of water is always going to be the same at temperatures, right? So the density of water is 1 gram per milliliter. So that's never going to change as long as we're at 25 degrees Celsius. Now, if we go and we make it a gas, then it's going to change. Whereas we increase temperature, we're going to have a slight change in temperature and in terms of density. Okay. Questions? Concerns? Yeah. Okay. Good. So let's see, how are we doing on time? We're doing pretty good. Okay, so if we look at the elements, right? You guys have your periodic table available?
Yeah.
Go ahead and pull them out. Okay, so we look at the periodic table. You guys can sit there on your sheet. You can actually tell me which metals are alkaline. Okay, so if you go to P table, if I just hover over alkali metals, it'll show me the metals that are alkali metals. It'll light them up in yellow. You guys are able to tell me because it does something very similar to you guys. If you look at the side of it, it actually tells you your alkali metals. What group is it?
Okay.
Group.
Oh, wait a minute.
Group 2, right? You guys remember? Top here, these are groups. Down the side, these are periods. Okay, so group 2. So group 2 metals are always going to behave the same way. Now, when we look at group 2 metals, PE, PE stands for what? Beryllium, right? So you'll notice that we use the symbol capital B, lowercase e. So that dictates beryllium. Now, let's say I had something like this. And I'm a new Chem student, and I do this. PO. Right? What does that mean? All right, sure. Lowercase p, lowercase o. Right? Because that doesn't this look like a lowercase p, a lowercase o?
Yeah.
Okay, so that wouldn't be anything to me, right? As the instructor, I'd mark you wrong because it means nothing to me, right? But if I had capital P, capital O,
Phosphorus, oxygen.
it's going to be phosphorus oxide, right? Okay, but if I had capital P, lowercase o, that's polonium, right? So we know that phosphorus oxide and polonium are not the same thing. They're two different elements, or actually, phosphorus and oxygen are two different atoms, and polonium is a totally different, right? So because we have two letters that are signify the polonium, we have to be sure that you write the capital and the lowercase. Right? And this is one of the most common mistakes that students make. And I have students that will do it from the beginning and try to do it till the end, right? And they keep getting marked off and keep telling them why it's wrong, but they want to challenge it, right? So your writing of the element is very important. You want to make sure that you write the element correctly, because otherwise it can mean something totally different. Something entirely different. Okay? Questions? Concerns? Catch? Okay, so you'll notice on your periodic table that all the elements either are a single letter, single capital letter, or they're two letters, a single and a lowercase. Okay. Now, some of the older periodic tables you'll notice here they have three, right? So those were undiscovered, they were kind of made up, they were just like, oh, these are kind of space holders, so we try to figure things out. So in the old days, they would put 3 when they didn't know enough about it, and then they would change it over to 2 when they got it stable for so long, and it's considered a real element. Okay, so you'll notice that you guys on your periodic table, you no longer have that case because those guys have been stable. They play with them enough so that they were able to get them stable for a certain amount of time. And so they're going to say, okay, we're naming it this time. Okay. So there's the possibility that there are going to be more elements when you guys are my age, maybe a little bit younger. The way science is going, it's probably be a lot younger. There are going to be more elements that are going to be occupied in the periodic table. So the periodic table is going to change. We have to stay flexible. Now, since we're talking about the periodic table changing, table. Okay, so if you notice, I clicked up here, it said Y, right? So periodic table really looks like this. This is what it looks like. So we have group 1 and group 2. These guys don't have a group number that's associated with it. Then you have group 3, group 4, group 5, group 6, group 7. Eventually, they're going to start naming these once we start getting more elements, right? They're probably going to change the numbering of them or something like that. But for right now, these guys, these are your lactanoids and your actinoids, right? So when we put it so that we can all see it on one screen, right? You'll notice you have this placeholder that's for it. That's what's shown in you. in your periodic table. Okay, so this here represents that placeholder. So these elements are going to be in what we call a different orbital. These guys are going to be in the F orbital, right? These guys are going to be in the D orbital. We'll talk about it, what it means later on. These last two really belong up here, right? So let me show you again. More sense. Okay, so now we got rid of that little gap. You'll notice, again, these guys are lined up with these, the LU, the LR, right? So these are really in a different orbital than these guys. Okay, you guys understand that? See that? Okay. And that's going to be kind of important to understand for later on. Okay, so I want you guys, so if I give you a period and I give you a group, I want you to identify the elements. The name and the symbol. Let's do period 6, group 13.
Five.
And it's yeah, it's TL.
Awesome.
Yeah, that's the hard thing about, yeah, remember lowercase, but capital. Okay. Let's see. Identify Mercury. Tell me where Mercury is located at. Which group and which period? Tell me the group first and then the period.
Group 12, period 6.
Okay. Okay. Tell me the period for because Mercury is a special case. Mercury at room temperature, even though it's a metal, at room temperature, it's a liquid. Okay, and so it signifies it being different because at room temperature, it's a liquid where most metals are solids. Okay, and there's more. Mercury's kind of even a special cases. It's the only ion, which we've not talked about, ion that is diatomic. So you need two of them when it's a +1 charge. So we'll talk about that. Okay. Let's see. Ruthenium. Ruthenium. Where is that located at? I'll see. I saw it, right?
So period 6, group 7. So RE.
Nope.
Say rhenium.
Ruthenium.
Group 8, group period 5. Yeah.
Okay.
And there's one right there, rutherfordium.
Yeah.
They also send.
Let's see. Tungsten.
Group 6, period 6.
Piece of cake, no problem. You guys got it? Yeah. Okay, so when we talk about measurements, we always have the number and we have the unit. Okay, now that's most cases, almost all cases, we're gonna have a number and a unit. Now, unit signifies what we're looking at. So So if I say at 5, I need you to be here in 5. What does that mean?
Your 5 minutes.
5 minutes, are you sure? You sure it was 5 hours?
No, that's our slang.
It could be anything, right? So without units, it could be anything. I don't know what the hell you're talking about. Give me an answer. It's like, okay, what is that? You know? So I need to know the units that we're talking about. So if I put 5 minutes, minutes represent what?
What's the time?
Time. If I put 5 milliliters,
Volume.
if I put 5 grams,
Weight.
mass. If I put 5 yards,
Distance.
okay. If I put 5 grams per cubic centimeters,
Mass over distance.
mass over distance, or not mass over distance, but cubic centimeters. Mass over volume, which is density. Okay, so units play a huge part in what we do, right? So you need your units. So when you're answering your question, you need to show me units, right? And a lot of times that's where we get you knocked off too. You'll be answering a question, it'll ask you something about grams per milliliter, right? But it'll give you something in grams per liter. So that means you have to do the conversion. So often we have to convert from one unit to another unit. So if you guys have your periodic table available, can you guys do me a favor and flip to the second page? I know we went over this yesterday, or not yesterday, last week. So if I have 25 centimeters, can I convert that to inches?
Yeah.
How?
1 centimeter equals 0.394 inches.
Said 1 centimeter equals,
Was 0.394 inches.
or I can also say that it's 2.54 centimeters. Do I have this right way, by the way? Oh, I don't. So then I would do the conversion, and then I would get inches, or I can go vice versa, right? So in science, we have a group of measurements that we commonly use, right? And that's called the standard or SI units, standard international units. So for time, it's going to be seconds. For volume, it's going to be liters. For mass, it's going to be actually kilograms, but we often use grams in our class. For distance, it's meters. Okay. And density, it's either cubic centimeters, so it's mass grams per cubic centimeters, or grams per milliliter. Okay. So those are going to be our SI units. You'll also find that we're using the metric system. Are you guys familiar with the metric system?
Yeah.
Anybody not familiar with the metric system? Oh, it wasn't showing you guys? I'm sorry.
What is the metric? Just like
Yes, it does. So let's talk about, yes, we use the imperial system. Right? Or we often will call it the United States customary system. Yes. I did talk about this, right? Yeah, okay, good.
How I would have to be under the king split.
Yeah. Okay, so as I said, the International System of Units, or SI units, or it's not actually called System International. Okay, so now this has been used since 1964. They always meet every so many years, and then they publish something out, and then this is the new unit that we're going to be using. It's pretty consistent. They don't change too much about it, but they do argue about every little aspect of chemistry. And then there's also going to be the IUPAC, which stands for the International. I have to look it up because I can't remember. It's for nomenclature. How do you name things? Okay, so these are the SI units that you guys need to be familiar with. Length is going to be meters, mass is going to be kilograms, time is going to be seconds, temperature, Kelvin, electric current, amp, here. Amount of substance, the mole, these are the abbreviations, and luminous intensity. The candela.
I've heard of that one.
You have it or you have it? It's not used that often. We often will get away with using intensity. Okay, so when we talk about those units, right, we have what we call the base unit, and we have the prefix. Okay, so the base unit for mass is grams. That's going to be the base unit for mass. Okay, I'm going to write them up on the side. I know that you guys won't be able to see it, but I'll put it so you guys can see it here in a minute. So base units. The time is going to be seconds. Or volume is going to be liters. The mass is going to be grams. Distance is going to be meters. And then you had all the other candles, all the rest of it. So when we talk about the metric system, we use those prefixes. So femto. Femto means 15, minus 15. So if you have FG, F stands for the femto, the G stands for grams, right? So this is a femtogram. So 1 gram is going to equal 10 to the 15 femtograms, or 1 femtogram is going to equal 10 to the minus 15 grams. Okay, you guys see that? Okay, so pico, right? Pico means 10 to the minus 12, right? So then 10 to the minus 12 picometers is going to equal 10 to the 12 picometers is going to equal 1 meter. And then 1 picometer is going to equal 10 to the minus 12. And so at the level that you guys are at, you guys need to know these, right? You need to know them at least to the femtom, right? Okay, so femtom, 15, right? Kind of makes sense. F, 15. Pico, well, that one doesn't make so much sense. Pico, 12. Nano, 9. Micro, 6. Mil, 1,000, right? 10 to the minus 3. Centa, 100, right? And then deci. Okay. So on the other end, so these are like all lower than our base unit. Okay. On the other end, these are all the ones that are higher than our base unit. We're going to add a couple more. So then we'll put them all up here. You know, so if we have hecto, is our prefix, so that's going to be 10 second, deca, 10, and then we know that 10 to the third is kilo. And then we know that 10 to the sixth is mega. And 10 to the ninth is giga. And 10, 12. Okay. So if I have a so the abbreviation for this is DA. So DAL means I have 1 DAL. How many liters would that be?
10.
Right. If I have H, how many liters would that be? Okay, you guys get it? Yeah. So those are going to be greater than. Okay, so see if you guys have a really good job of remembering them or not. And then play a little game. It's going to be high or low. Okay, compare it to 1 second. High, low, or equal? Is it higher than a second? Lower than a second? Lower. Or is it equal than a second?
Lower.
So Pac-Man equals greater 1. Yes or no? The arrow points to the small one.
The alligator.
The alligator, thank you. The alligator. Okay. I have to remember that because I used to use Pac-Man. Pac-Man. Okay. So let's do higher or lower. Okay, this is gigasecond, right? Let's do one more for the road.
Lower.
Questions? You guys had it look. Some of you guys had it look.
Is that in nano?
Nanos, yes. Got it? Okay, so think. So things that you want to remember, put up here somewhere, right? So we often will use the units, the SI units for the meters. Again, things you want to remember, right? Well, you don't have to worry about the North Pole, right? But you do want to remember the speed of light. So the speed of light is going to be 1 and basically 299,792,458. So 3 times 10 to the 8, right? Is that right? Roughly, we round it. 3.00 times 10 to the 8. 1 over, okay. So that's going to be the speed of light in the back. Okay. That one you're going to see again and again and again. Speed of light is always consistent. It's always going to be the same. So speed of light is always going to be equal. If you look at it, it's going to be 3.00 times 10 to the 8 meters per second. So a meter, right, it's going to be equal to that. Okay. So and you also know that how many yards are in a, I mean, how many inches are in a yard? Okay, 36. How many yards, how many inches are in a, how many inches are in a meter? What's that? Yes, 39.37. Where did you find that at? Wow, you know, it's that paper, right? So, and if actually look at a meter stick, it actually will go to 39. Okay, so here, there's meter, there's yard, there's centimeter. These are relative because this is a white and yard. A little bit bigger. I mean, a little bit bigger. Okay. So we'll recognize that a meter is slightly bigger than a yard because a yard is only 3 feet, where a meter is 100 centimeters. Right? Can you guys do that math to prove it to me?
Have to convert it, take a while though.
Why would it take a while?
I got right eye.
Oh my God. Prove it. I want you to prove it. So if we do the math real quick, we said a yardstick is 3 feet, right? So we have 3 feet. 3 feet equals 1 foot equals 12. 12 inches equals 1 foot. Right? So three feet, 1 yard. Yard. But 12 inches. And we know that an inch equals 1 inch equals how many centimeters?
2.54.
Okay. You can do the heavy lifting for me. 3 times 12 times 2.54. You're going to cancel out. You're going to cancel out. Wow.
Is that 91.44?
91.44. And we know that 1 meter equals how many centimeters? Cancel out. So a meter stick. You guys didn't yell at me for not putting my units. Come on now. Okay. So we know a meter stick is longer than a yardstick, right? We just proved it right there. Okay, by our conversion. Piece of cake, not a problem, right? So this is going to bring us to that analysis. You guys have already done, dimensional analysis and everything like that. Today, you guys are going to be doing a measurements lab, the rest of it, and then also some numbers and graphing and all that stuff too. Okay, so if you guys have your labs from last week. Okay, so the one thing that I want to talk to you guys about is uncertainty, right? There's going to be a certain amount of uncertainty associated with measuring, right? Because we're going to say, well, it's between these two numbers, so I'm going to guesstimate it's about a half, or it's about 0.4, it's about 0.6 or 0.8, depending on where your eyes are telling, you, right? That's gonna be a sort of uncertain, right? And when you're dealing with uncertainty, you have to take it into consideration, right? How uncertain you are, okay? So often, to help us deal with uncertainty, we use what we call significant figures. Okay, so I told you guys, I don't know if I told you, maybe I told you. Did I tell you about tender spiking left and right?
Yeah.
How much I weighed? Anybody remember how much I weighed? Okay, I weighed 220 pounds according to my scale, right? My scale, right? Now, if I went to your scale, I may not weigh 200. I may weigh a little bit more, but on my scale, I weigh 220 pounds, right? I weigh 225 pounds on your scale. But then if I go to Chrissy's scale, I may weigh 223 pounds, right? So if I go to your scale, I'm gonna have a different weight than if I go to her scale, than if I go to Raul's scale, right? So then all of them I need to take into consideration. If I want to have an idea of how much I should weigh or approximately, I have to take them all in consideration, right? So when I get on the scale, you guys ever played with scales?
Yeah.
Right, so you guys will do that today. Have you noticed how that last number fluctuates?
Yeah.
Right? Oh, it's a 2, oh, it's a 5, it's a 3, it's a, you know, it fluctuates. That last number always it fluctuates quite a bit in this case, right? So that number there is not certain, are you sure about it, right? It didn't stay on that one number for a while, it always moves. If you get it back on there for a minute, you're like, okay, now I'm 1 pound less. What do you guys report down? You report the pound that's less, or you report the pound that's more?
That's less.
That's less, right? Because we're like all trying to get skinny, right? So we all get on that scale and we're like, okay, I'm 220 pounds, I told you, right? So 220. But it also told me that I was 225 just a second ago. 225. And then, as I told you, when I went to your house, how much did I weigh? 220. And then when I went to Chrissy's house, how much did I weigh? 223. And then when I went to Raul's house, how much did I weigh?
240.
240. My numbers up. Okay, so, but all of them were different weights, right? But if you look at the numbers, except for Raul's numbers, this was all screwed up. I couldn't weigh that much, right? So if you look at all those numbers, those first two numbers are exactly the same. They're both 2, 2, right? It's just that last number, the ones in that one spot, is fluctuating, right? So where's the uncertainty at? Is it in that hundreds, the tens, or the ones? Ones. Okay, so that would be our uncertainty. It's in the one spot, right? So in this case, we're saying, I'm not so sure about it, right? So I'm going to give Dr. Henry the benefit of the doubt. So I'm just going to put a 0 there because none of these are over 5. They're all under 5 except for the one that was right at 5, right? So I'm giving Dr. Henry the benefit of the doubt, and I'm saying he weighs 220, where this number here is unknown. Can you guys see that little drawing over there? Let me put it over here so you guys can see it a little bit better. And then, can somebody do me a favor? This was my little thing. Okay, so let me stop. Otherwise. I like screwing things up. I screw it up naturally, so I don't need anybody to help. So. Okay, we're ignoring this one. No.
Outlier.
You better get a better scale. Okay, so if you look, like I said, these two numbers are exactly the same, right? They're all the same. It's just that last number here, right? This is the one that is the one in question. So that's the one that we were questioning, right? So you're gonna give me the benefit of the doubt since they were all under, right? Under 5, or most of them were under 5. So you're gonna say 220. This number here is uncertain. So we put a 0 there because we weren't sure about it. Now, if we put a decimal point there, we're saying, I know for sure that I weigh 220. But since we don't put a decimal point there, we're saying this number here is questionable. we're not sure about it, right? So it could be anywhere from 0 to 5, right? That's what we're saying, essentially. Okay, so that's sig fig. So in this case, it has two significant figures. These numbers here are considered to be significant, where this number here is insignificant because we're unsure about it. Okay, now let's say Raul was kind of close to the real thing and we start doing more weighing, right? We go and we weigh at somebody else's and he gets me 239, 238, 236. So, and ignore this for right now, we're looking at these down here, right? So they're all, right? The number here, these are all 36, right? But all of these numbers are greater than 5. They're higher than 5, right? So I would look at this and I'd say, oh shit, maybe I'm closer to 240, right? So then I round up because all of these are greater than 5. Because again, this is my uncertainty. They're all greater than 5, so I'd say 240 would be more likely. Okay, so these 39 would be rounded up to 240, right? Again, this here lets me know it's either 39, 5 or greater, or 40, less than 5, right? So it gives me that nice range. Okay, so again, this case would also be two significant figures. This one we're unsure of. Okay, so it could be numbers that are all the way up to 5, or it could be numbers down here at 39, 239, 238, 237, somewhere down there. So we're not sure about it. Okay, so we'd also say two sig figs. Now, don't mistake sig figs for what it means, right? It's still 200. I'm still 200. I'm not 24, right? Not 24 pounds. I'm still 200 pounds. And this is either 40 or it's 30 or it's, somewhere in that range, right? Or 45, but it's 200 and something. So this is just a space holder, but it lets me know that this number we're unsure about. Does that make sense? Okay. Now this happens a lot in science because not all pieces of equipment are equivalent, right? Sometimes we got shitty scales, sometimes we got good scales, right? So Raul may have that not new fancy, it tests your water weight and all that stuff, and does everything for you, right? And where Christy had the old scale where you actually had to sit there and put the weight and balance it out and stuff like that. We have one of those in the back, and so one of those weights, right? So then in that case, they're going to be two different equipment, but you're going to be taking data from all types of people that are going to have all types of equipment. So you need to be able to sit there and take into consideration their error or their uncertainty. Okay, does that make sense? Yes.
If all that data was grouped together, would you have two unknowns and tens, or would it still remain in the one?
That's a good question, right? So if all the data was grouped together, we would have two unknowns, right? Because we have 30s, we have 40s, and we have 20s, right? So then the only thing that we could say is that it's here. So then really, if we were looking at all the data together, all we can say is that 2 was right, and then we put zeros and boom. And I would like that even better, because then I can say on my Tinder profile, I'm 200, right? So, so that's a good point, right? So that's also why you kind of look at your data. Your data tells you a lot, right? So you guys got a chance to play with a lot of data, right? Don't worry about it, you got a chance to play with a lot more. Okay. Let's go ahead and take a break. Is that okay with you guys? Because I need a water break. It's hot and bothered here. So talking about sig figs just gets me over it, So we'll say 15 back. And I'll also give you a chance to go get my stuff out and try that. Yeah, you can do that. Yes. Yeah. He's fixed. So we'll take a look at this, right? So we have size. This much. And we know the thickness of the ice. So if I was thinking about that, so the whole thing is. And then how much of it is occupied by ice? Only that much is ice. There. So subtract that. Right, because then that tells me how much is occupied. So then that gives me the area. We are. Oh, yeah, the density. We also have this. Centimeters. So. Yeah, so this is my square. We have to make it square. So we start at 7. Square. Bless you. For kilometers. So for the roads, so 6.5, 6, and it's square, so we're gonna have square. Okay, so that gets rid of our square, square. So now, square. We'll start off with how many meters? Split that. So then we have 1,000. Split it. Centimeters. So square, then how many centimeters? 1,000. I'm just. Square. So then, we're square, skip. So then you just get this square, this square, this square. That's going to be my answer. Square. Now, we also have to multiply this one with this here. So then I have to multiply it by its thickness. Which is 8 centimeters. So, okay, that's set up. Yes.
So I want to let you know that I may have to leave a little early, like around 3:50. I didn't know it was gonna go to.
Okay, that's fine.
Appreciate you. You gotta do it. You can tell the harvest gets like 60. It's from all the conversion. Small.
Oh,
What is this? Let's do today.
Back to learn.
Back to learn.
Back to plugging the pseudomorph. I'm gonna get extended.
Oh,
Oh, I gotta make sure.
Actually, it may extend a little bit longer since we gotta finish chapter 4. Planning to finish it last week, but actually took us a little longer than anticipated. That's one.
Dr. Henry, do you listen to rap music?
I do.
Do you know who JID is?
JID.
JID?
JID?
You know who J. Cole is?
Yes.
So JID is on Dreamville, which is J. Cole's label.
Okay.
And he just dropped an album. But the main reason I bring it up is there's a song on the album, it's called Money. It just talks about like how much he cares about money.
That sounds familiar.
Just check it out.
Okay, so last we left off, we had a whole bunch of tables last week, right? If I remember correctly. Did you guys do the calculate the totals? Somebody write them up for me. Shouldn't give you a sharp, it's right on the door. Any volunteers? Yeah, Anybody write down the total? I have it right up there. Total.
Oh,
Yeah, I wrote it. That's so right, because I was going to take a picture of it and I'm sorry. Okay. This is the number of volts. On fire. Yeah. That's the night. But did you guys generally, I mean, we all label our stuff a little bit differently. For the most part, were they labeled kind of the same, or did you guys change the number? Kind of, you have to understand. Okay, so how many of you guys are left-handed?
me? Oh,
Two. Two. Anybody else? Just two, okay. So I'm gonna make a prediction, right? So one, two. Left. Then we'll go 4, and then we have 5. 7. Let's do your application. Lefties, always do my application now. Majority of the time, I'm doing that thing. Okay, so if we looked at the data, and if we saw this time, okay, where we had 3 here, and we had be here, right? And 3 year, and then high numbers over here, which is what we primarily see, right? If this is number 1, 2, 3, 4, 5, and then all those 6, 7, 8. That's it could be 6, 7. There's a tendency of right-handers struggle getting things done on the left-hand side. The left-handers will normally get there. Your data is really it's different, right? So if we take a look at it, number 1 was the most common hit, right? Number 1. Right? Then we would say it would be the whole. Because we're on fire. That's what we wanted to get, right? And then it was number 2, number 3.
That was number 3 first.
Number 2, right?
Number 3 first.
What was that?
Number 3 has more.
Yeah,
So-
number 3, number 2. So that those front is triangle here, right? And then when we get to 4 and 5, less. And then the ones down here were less. Although 6 is interesting. It's like 7. Yeah, it doesn't matter. But you can look at the data. The data can tell you a lot about what's going on, right? That's what part of this is. Data. So based upon that data, what can you say?
From the data, we got a lot more right.
The one that, 5 or 6,
So we have a better chance of hitting a 1
then a 5 or 6.
or 5 or 6. Okay. What else can you say?
Can you bluntly say that you have more right-hand shooters than left-hand shooters because of the data?
You can suggest that. I
Suggest.
mean, you have, although, like I said, this one data point here, right here suggests, something with that corner there, right? So even righties have struggled with that. It would suggest that you do have more lefties than righties because that data point right here. And then all your other numbers here, more, lower, right? Compared to here, except for that one. This is the anomaly. What else can you say?
The nearer the cup, the higher probable it is to make the shot.
So the closer the cup, the more probable you're gonna get something in, right? And although like you guys were on fire with your bowls, right? Your bowls are like close to, really close to that number 1 cup, that number 1 cup bowl. So again, from the data, you can tell a lot of things. One of the other things is that we can also tell how accurate you were shots, right? So if we have the total number of shots, somebody do me a favor and add all these up.
120. Yeah, 120.
120, okay, so we have 120, so that's our total number of hits, right? And then how many total shots did we do?
192.
Okay, so we have to do a competition between firewall and, so you guys can give me an idea of the percentages there. So if it was 100%, we would have got 192 in cups, right?
Yeah.
So then, in other words, how many did you miss? It was 72.
Yeah.
Like 62.5% accurate,
It was how much?
62.5% accurate.
So we'll say precise, right? Because that would be precision. Cups. So accurate would be
That's the intended target.
so it's gonna be like 9 something. Right?
Yes, 9.375.
So in terms of accurate, you guys are 9%. Give or take. Okay, so now if we looked at the data compared to the number of hits, number of things that landed in the cup, right? We'd expect our accuracy to increase, right? So instead of saying 192, we're going to say 20. So 120 out of sorry. Just yell at me. Don't be shy. Say, Dr. Henry, I can't see from way over here. So if I go 18 divided by 120.
Only got a 15%.
Yeah.
So now this is another example. So science, it is, you always want to try to, best way of saying this, you want to show, put the best foot forward always, right? Okay, and you want to be accurate about what you say, right? Okay, so now we know that we were, what was it, 9% accuracy, right? We had 9% accuracy overall. But if we talked about, let's say, the number of hits, with the number of hits, you guys were like 15% accurate, right? Now that 50% looks better than that 9%, right? So then you would show that data, right? They have access to all that data. If you were trying to hub somebody, trying to get somebody to sell you something or something like that, which would you use? Would you use that 15% accuracy or would you use that 9% accuracy? At 50%. But then how would you explain it so that you could get away with using it and not be lying to that individual?
Clarify, was that of the 120 shots that we did hit?
So out of the 120 shots that were in cups,
Where the bullseye?
15% were accurate. Bullseye, right? And so that way you're not lying to your reader, right? You're just putting your best foot forward, right? Okay. Now, science is always about really putting your best foot forward because you want to get your next paycheck, right? That funding. Now, but you also want to, set, overall, there's 192. Put that in there. We threw 192 balls, right? And then you write that lower in the discussion and everything like that. Out of 192 balls, 120 of them were actually hit. Of those 120, 18 were actually, in the hole where we wanted it to be, right? So you always want to put that cell. You also put that in there. You just kind of bury it, right? And often what you buried in, I hate to say, but a lot of times I tell you, I look at the conclusions. A lot of people don't because that's the end of the page, right? So they usually look at the abstract, which is usually a summary of what you guys are going to talk about and everything like that. And they'll maybe look at a couple of graphs, and that's about it. But a good scientist will read the conclusions because the juicy goes in the conclusion, right? So you're going to put stuff like that in the conclusion. As a good scientist, you want to sit there and always get the best foot forward, but you want to make sure you're accurate, right? And what you're saying. You don't want to missell things, right? So you were going to use that 15%, and that's probably what you're going to show in the figure, because again, people tend to be lazy. So you're taking advantage of their laziness partially, but you're also being a good scientist because you know your next paycheck is going to be dependent on the data that you get, right? And so you're doing both, but you're being honest with them because in the conclusion you say, yeah, of course it would have been better if we were more accurate, right? Overall, we missed this many balls. But as a whole, you take into consideration the number of hits, you did a pretty good job. So you just sell it that way. Okay. Now, the other thing that we want to do is it's how you show the data and how you present the data. Those are the two important things, right? Showing the data, presenting the data. And then also, when things don't go as planned, how do you write it that way, right? So is 15% good? Would you guys accept 50%? If you're bond, I'd accept 15%. But, anything else that you accept 15%?
No.
Right? So you'd be like, so you always want to give them reasons. Okay, so this is why this happened. Or you would say, the data, there's not enough data points to sit there and make an educated decision on this, right? Sell it short. We need more data points. We need more time. Right? So, or it can be not significant. Okay? So would 15% out of 120, would that be significant enough? Or would you guys like to have more data points? Maybe have beers involved. More data points. So with beers and without beers, right? Because that could be a factor. you may loosen up, because I saw some of you guys in the beginning, you guys were so tense. And then all of a sudden it was like, and I'm like, towards the end, I would say that you guys got better than towards the beginning. Would you guys say that?
Yes.
She said, no, I was bad in the beginning, I was bad in the end. She's like, "Oh." But if you had a couple of beers, maybe that beer would relax you. But if you have too many beers, then what happens, right? Right? So all of those are different aspects of the experiment. You've done one experiment, you guys can sit there and design another experiment to sit there and test it out. So like on the weekend, you're like, hey, we're studying precision and accuracy. So we're gonna get fucked up today, and so we're gonna get fucked up, you're gonna be buzzed, and you're gonna have to stay sober, right? And then we'll do a comparison, right? So you can replan that experiment and get that data. And so again, the data can tell you stories, right? But you want to be sure of what it says. Now, based upon what I see here and what I saw at Fireball, their numbers were like very similar. Only thing, I'm not kidding, none of them were lefties. All of these were all really low numbers on this side. On this side of the table, everything was low. All these were high, right? They had a medium, theirs was lower than your bullseye. You guys had a better flow. And their front three was exactly the same, really high. Front three really high. The bowl was like a little lower than the front three, and then, but these were like 1s and 2s and 3s over here, right? So immediately I said, first thing that popped in my mind was what? Lefties, right? Because comes over here, they're gonna struggle with, where a lefty, not so much, right? You guys had 2 lefties, that improved your odds because they had none. Quite a bit. And you have 2 lefties that I'm guessing that are beer pong players, right? They've been at a couple of parties, they turned up a little bit. I'm just saying because they pulled their weight and did some, So, okay. So, and then that's also what I would probably write in this little discussion here would be like, and our lefties are bomb. They must be real beer pong players, experts, won a couple of tournaments there. Okay. So the next thing that I want you guys to do is calculate the standard deviation. So if we take all of these and take the average, right? So if we take the average of that, so our full number is, what was it? You said 120, right? 120 divided by 10. Okay, so our average is 12, right? Okay, so if our average is 12, and then if we're calculating the standard deviation of all of our values, right? So then that's going to be our value minus our average over the number minus 1. Okay, so subtract 12 from all of these. So now, a deviation allows you to know, so if you have your average, our average is 12, it allows us to know on both sides of the 12. And so we can represent all of the data by looking at deviations, right? So it's kind of like plus and minus. So it's the plus and minus of that 12 of that average. So have you guys seen those curves? Called the bell curve.
Oh, yeah.
Yeah. Like that, right? And then, so the average can be represented by that, right? That line in the middle. That's going to represent the average. The deviation, a standard deviation. So your standard deviation represents the distance of that average. So if we said the average was a C in the class, this range is where your C's are going to be, right? And so if we go beyond that range, then deviations are going to sit there and represent, okay, that's where your P is going to be, the average of your P is going to be, right? And then if you go beyond that, that's going to be where your A's are going to be, right? So, and that's the same thing over here, So a deviation here just represents your averages here, it's gonna be plus and minus of that C, that middle grade C, right? And the deviation will be off to the side and off to the other side. Okay, so that's what a deviation is. So if we sit there and we took 12 minus 12 from all of this, this would be 12 minus 13, right? 4, 3, -5.
That's 5 on number 3. On the third row, it's 5, not 3. 17. Yeah, right
Oh,
there.
7, sorry, thank you. 5. 12 minus 5, minus 9, minus 9. That would be 1, 3, minus 3, and so if you add them all up. Guys, no standard deviation. Yeah, that is crazy. I've never seen that.
Yeah, it's different.
But adds up to 0 exactly. Okay, well, you would normally be able to calculate a standard deviation, but you guys don't have a standard deviation. So that's a first. I don't know what to say. Caught me off guard. Okay, so but that's how you're going to calculate your standard deviation. And it's also written in your lab for other things. And so your guys' standard deviation is 0, so you really don't have any deviations between your. You guys did pretty good. I guess you got expected data overall. You know? So anyway, you guys to kind of help you guys with some data stuff.
Yeah.
Okay. So now I need you guys to get in your groups. You guys have your labs with you? Okay. So there are 2 parts of this lab. Part of it requires you using your computer and you guys graphing a line. You guys want to try that yourselves, and then we can meet here on Wednesday with everybody brings their computer. Right, because I know we get your computer today, and I can tell you this. Right, but the other part of the lab actually requires you to do stuff in the lab. Let's do some stuff in the lab, right? You guys are gonna have a couple of unknowns. So I'm gonna give you guys these cubes. Now these cubes have tape on them to cover what they are, but otherwise you know exactly what they are. So you're gonna have to determine their density. So I need you guys to talk to me, right? You guys know what density is?
Yeah.
What is density?
I was just said yeah.
Well, you can't say yeah, it's not. Tell me more. Tell me more. Somebody said it over here. I heard it. Say it again. I can't hear you. Can you hear over there? What did she just say?
No, you said it.
Mass over volume. You guys can hear it. I can't hear you. Yeah, I told you. Right? Okay, so it's mass over volume, right? So you guys are gonna have to be able to calculate the mass and the volume. So how would you be able to calculate the mass and the volume of the cube?
Scale.
You weigh the cubes? Okay. And then, so that would give me the what?
Mass.
That's gonna give you the mass. And then the volume, how would I be able to calculate the volume?
Length with the length.
Length times width times height.
Oh, so I can use it. If it's a cube, I can use length times width times height. And if it's a cube, then my length, my width, my height should be exactly the same.
Yeah.
So that's one way of doing it. Is there another way to do it? Water displacement. Yes, we can also use water displacement. So we can have a graduated cylinder like so, maybe not so big, right? You have a little ED one in your boxes, right? So then you're gonna drop your cube, or you're gonna put some water in there, you're gonna drop your cube in there, and then it should displace, right? Okay, so what I like you guys to do, I like you guys to do it both ways. I like you guys to calculate the volume both ways. One with water displacement, and one while you guys drop it in the cube. Now, you're gonna get 2 cubes, then you're gonna have to identify the cubes by their density. How are you gonna be able to calculate the density of a cube of metal? Or how are you gonna be able to find the density of different cubes of metal? all metals are the same density because that's one of their, what properties? Physical properties. Okay, so it's one of their physical properties. Density is one of their physical properties. We also know that the density is an intrinsic, extensive. Okay, which means
It's subject to. Depending on its state,
what do you mean by that?
whether it's a solid or a liquid.
Okay, so it could be dependent on temperature, right? But it's got to be consistently the same if it was a solid, right? So if I have a ton of iron and I have a small cube of iron, its density is going to be exactly the same. Okay, you guys want to give this a shot? So you guys are going to each get 2 cubes. Do you have your groups? Do you have your road dogs? Okay, so what are the groups? We have 4 colors, right?
Yeah.
Okay.
Wait, so all of it?
Yeah, I think so.
Let's put it to those little itty bitty groups of two.
Yeah, you're gonna work together as a whole group. Unless you don't want to, you know, if y'all like each other, let me know. Let me know now. It won't make too much of a difference. I'm still making you working together. But then I at least laugh at when you guys argue and stuff. Okay, and the other thing is that sometimes I think these companies, I think they're shady, you know? Some of these companies and they tell you, oh, we gave you this, right? And we gave you this back, right? And that's not quite what they said they gave you. So you guys are actually confirming that. You're doing a twofer. Okay, so that means that you guys have to get your lab kits. Okay, which group is Rich?
Our whole group, this is group yellow.
Oh, this is group yellow?
Yeah.
Oh, the whole group is group yellow.
Yes.
Okay, so what we'll do is whole group yellow, we'll have you guys do 4 of them then. So then that way you guys can split up 2 groups and you guys can compare your results.
Do I
Okay.
do, like,
You're with group yellow.
Yeah.
Yeah, we're gonna put you with group yellow. So I think, because I think they had less than everyone else.
I think we all had 3.
You had 3
Just everywhere though.
or 6 per.
6 per table. Okay, well, you're 7 today, right? You got a new one.
You're part of our side. Either way, we're all working together.
That's right. Actually, I'm gonna take it back. So we just have 5 and 3. Otherwise, I won't have enough. Eventually, one day, it'll be here. My order comes. Okay. Okay, you guys, need to get your tools. Oh, they've been moved.
So for the last, or is it all inside?
Your class is gonna be, it's gonna be L1
Yeah.
or L2 or L3. That's what you guys are. You guys are gonna be located at L1, L2 or L3. Or here.
what section? Get the.
One.
Or L2, it doesn't matter, they're all,
L5, L7.
yeah, they're all the same, you don't have the same.
L,
They're on the.
But you guys are assigned a particular one.
Yeah. Oh. Yeah, right there.
Let me figure out. I read. See, the missing water.
It's right there.
Oh, there it is.
Yeah, and so next week, if I get to
Oh,
it,
yeah, we're.
rather than many things I've been trying to get to, you guys will get an inventory list of everything that's in your kit.
Is there a two AM?
And then you'll also, it'll be long.
This one's
You'll have
already
a,
on it.
Oh, no, it's-
a code that's in there. You wanna write down your code or?
1A005C2 is the last bit in here.
two?
Yeah.
Yeah, that's probably ours. Oh, there's one.
Okay, so you guys are given, we have waybooks, so you can get some little waybooks. So put the metals on the waybooks, don't put them directly on the scale, because otherwise they react with some of the stuff that's on the scale and then that will change the weight. See those cute waybooks? Little cute waybooks.
Unless you want to use that picture.
Yes. That's a, yeah.
Oh, this one right here.
The waybooks,
This one, right?
yes, that's a big.
Yeah.
Right.
Yes, the little one.
See who's there with this?
So you just put the-
Right, go ahead.
And
I guess. Are we supposed to have two keys or-
No, so you guys are sharing it too.
Oh, okay.
So,
I would ask.
So for this, is it supposed to be placed on this packet or?
yeah, it's in the packet. It's towards the back. So the first two are what you're gonna be doing with the computer.
Oh,
So the second part is the meniscus. So if you guys take a look on page Bucky. Okay, yeah, it's a long packet. On page 7 are the instructions for part 4, part 5. Right? So if you guys look at the over here and over there, we have 2 scales, right, on both sides. So we have this is called an analytical scale. It's going to be very precise, right? Or it's going to be, it can be accurate too, but it's going to go out more decimal places. This here is called a decimal scale, right? So it's going to, when it's working, and you want to make sure that it's on pounds, I mean, not pounds, on grams, and not pounds or. Okay, this here is called a deci scale, or actually this is a centi scale because it's a centi. It's 2 decimal spots over, it's in the 100 spot. That one there is a deci scale, the one right over here. It only has 1 decimal point and then there's 1 over. This is the deci scale. So you're gonna weigh a 50-pound weight. This is your 50-pound weight. There's a 50-pound weight over there. You're going to weigh the 50-pound weight to make sure that how accurate the scale is going to be. Both the deci and the analytical scale. You guys are going to be using deci. I mean, not the deci, the centi and the analytical scale over there. Okay, and just make note that you're using the centi instead of the deci. Okay. So that's gonna be the very first part of it. You're gonna weigh this guy. And then you're gonna weigh your little, you guys have these little cubes of unknowns. So you have 2 cubes, you need to weigh them twice, and then you also need to take volume of twice. So what I recommend is that one of you guys do it and then the other two do it. And then that way you guys can. Okay. So you guys got two?
Probably last Monday. The lab 3 package.
Was it on the day of so we just,
I was in there. I think that's it. Because I got it.
Wednesday?
I think you guys got it.
Yeah.
Yeah.
I'm doing about the same day with your point. That's the day.
No, that was after.
No,
We did, we did.
It was at the beginning of class time. Because I wasn't here at the beginning.
I was confused. I was like.
So you're gonna weigh them on the boat, so you're gonna throw out the little boat thing first, and then get the weight of it.
Dr. Henry,
Yes.
I need a package. I didn't get one.
You get one?
So I think, so what he said is, they do one, then we switch. We switch, and then we switch to there, we just compare.
Did you get one? Oh, yeah, you got one.
Let's start on page 8.
Where's the part 5?
Oh, that's a description of what to do.
You can do that.
Okay, he's the.